Ready? Good evening and welcome. My name is William Harris. I'm President and CEO here at Space Center Houston. I'd like to extend a warm welcome as well to those watching live stream. We're actually streaming this program live tonight on Facebook Live. Through this Thought Leader series, we engage space exploration leaders in stimulating discussion and provide you with an opportunity to participate in the conversation. Space Center Houston strives to create a community of problem solvers and fuel the STEM pathway to advance a science and engineering literate society. We are the official visitor center for NASA Johnson Space Center and also a Smithsonian affiliate, which enables us to bring to the public current and historic information on space exploration and artifacts from the National Collection. The pre-programmed slides you saw as you were coming in this evening highlight but a few of the many programs and activities that we offer here at Space Center Houston. We invite you all to become involved. Please consider a membership to our Science and Space Learning Center and join our many fun and learning experiences. We are a nonprofit organization, and so your support provides funding for our education programs and is tax deductible. You can learn more at our website, which is spacecenter.org. I also want to take a moment to acknowledge our incredible board of directors here at Space Center Houston, who enable us to offer quality programming to the public. I'd like to ask Alon Miller, our board chair, and other board members to stand for a moment and be acknowledged. Please stand. Thank you so much for your leadership. So, the countdown is underway for the 50th anniversary of the historic Apollo 11 mission to the moon. In celebration of one of humanity's greatest achievements, Space Center Houston is offering a year of exciting events and programs. In fact, Houston has designated the month of July Defying Gravity Month. You can learn more about what's happening on our website, and also very soon the City of Houston will be publishing a calendar of events and programs happening throughout the city to recognize this incredible achievement of humankind. So, during his State of the Union address on January 25th, 1984, President Ronald Reagan directed NASA to build an international space station within a decade. Tonight, on the eve of the 35th anniversary of this speech, we'll take a closer look at this magnificent space hardware, true engineering and science marvel that we all admire. Following remarks by our presenters this evening, I'll pose a few questions, then we're going to open the floor to all of you to ask your questions. So that those on Facebook Live can also participate, we ask that you email your questions to the address thoughtleaders@spacecenter.org. And that will also be up on the screen to remind you later in the program. Though I do want to take a moment to ask if do you have any kind of a mobile device, if you could please put it on silent or turn it off so it doesn't interrupt our program this evening. I'm very delighted to welcome our two distinguished speakers, Mark Mulqueen and Dr. Scott Copeland, both with the Boeing Company. Mark is Boeing's program manager for the International Space Station. The ISS is the largest and most complex international scientific and engineering program in history. Mark leads the Boeing team in its key integration role for NASA's ISS program, and his responsibilities include overall integration and operations of the ISS orbiting laboratory. He's also responsible for providing sustaining engineering, expanding scientific and exploration utilization, and implementing vehicle enhancements. He is the senior site executive for the Boeing Houston site. Prior to this role, Mark served as deputy program manager for Boeing's Commercial Crewed Transportation System program, and he's also held positions as deputy program manager for ISS, vehicle program director for ISS, director of the Mechanical Structural EVA and Robotics team for ISS, associate director for mechanical design at the Boeing Rocketdyne facility in Southern California, and deputy director for the ISS Power Module team. Mark joined the Boeing Company in 1985 as a structural engineer in the Rockwell North American B-1 bomber program, where he contributed to fuselage and flight line liaison engineering support B-1 production operation. He's a graduate with honors from Cal Polytech University in Pomona with a degree in structural engineering. He's also earned degrees in applied mathematics from Cal State University Northridge and a master's of business administration from University of Phoenix. I'm delighted that Mark also serves on the board of directors of Space Center Houston. Our other speaker is Dr. Scott Copeland, who is the Senior Manager for Research Integration on the International Space Station and co-founder for the Boeing Genes in Space Molecular Biology STEM Education Competition. Scott has more than 34 years of payload integration and hardware development experience, supporting multiple NASA programs. He also served in systems engineering and integration, payload integration, engineering, and safety programs. He developed flight support equipment for transporting spares to the ISS via the space shuttle. Prior to joining Boeing, he spent 14 years at Teledyne Brown Engineering in Huntsville, working on the NASA Space Lab program and various positions, including program management of 3 Space Lab missions. He completed his BS degree and master's in mechanical engineering from Auburn University and is completing his PhD with an emphasis in solid mechanics, performing research on solder joint reliability of microelectronics, that's a mouthful, exposed to space or high temperature environments. So this evening, Mark is going to provide some insights about the International Space Station, and Scott's going to provide us with some highlights on the science and research aboard this national laboratory, which just happens to be in space. So, without further ado, please join me in welcoming Mark and Scott.
America has always been greatest when we dared to be great. We can reach for greatness again. We can follow our dreams to distant stars, living and working in space for peaceful economic and scientific gain. Tonight, I am directing NASA to develop a permanently manned space station and to do it within a decade. The space station will permit quantum leaps in our research in science, communications, in metals, and in life-saving medicines which can be manufactured only in space. We want our friends to help us meet these challenges and share in their benefits. NASA will invite other countries to participate so we can strengthen peace, build prosperity, and expand freedom for all who share our goals.
It's really amazing. 35 years ago, the foresight that President Reagan was able to share with the United States citizens in his keynote speech, and it really led to what we see today and what we've developed. Before I get started, while the partial government shutdown has not affected the Boeing ISS teams, we are concerned about the short-term effects of our friends, families, and neighbors in the communities we operate in, as well as the long-term effects that may begin to weigh on our operational efficiencies or pose other challenges for our businesses and for the space and aviation sectors. We urge the administration and Congress to reach a solution to this funding impasse quickly to fully reopen the U.S. government and preserve our economic growth. And so, as we get started here, that's mine. I kind of wanted to sit back and just kind of recognize that as we have developed, I think William introduced me. I started in '87 on the International Space Station program, virtually the beginning, one of the original teams that were assembled. When NASA first responded to the President's challenge, they built what we call the power stack, and it was very interesting of their concepts in the early days there because they had all the mass down close to the Earth. They had the big power where the arrays were further away, but the thing was probably unstable. It was probably an artist's rendering of what they thought the station would look like. It has, of course, crew modules and things associated with it, but it probably didn't have a lot of engineering associated with it. But it did set off the challenge with NASA, probably about two years for them to develop the RFPs for breaking down the space station into a main truss segment, which also had command and control, pressurized modules where the crew would live, which had life support systems. We had the electric power systems, which were generating, their goal was 120 kilowatts, both energy generation and storage. And then they also had, what you see in the upper right there is a little orbiting platform. They made this dual keel system, and they thought that they would be able to build space platforms out there, or satellites in space, and we'd use space station for a relay for eventual deep space missions further away from low Earth orbit. So they're really thinking ahead, and if you think of what we're talking today with the Gateway and other things, communication to deep space is always a problem. It's always got delays. We know that. We talk about our rovers on Mars and everything. You have 20 minutes delays or more. So they're really thinking ahead. It turned out they had an audit, and they said, okay, let's evaluate your concept here, this dual keel concept. And it turned out they felt it was too difficult to assemble and build. It'd take too many launch missions, too many shuttle or other rocket missions. It'd take too many EVAs to assemble. And so NASA quickly kind of morphed it into more of a streamlined one here that's showing up upper left for you. They got rid of the dual keel, it got rid of all the extra communications, and they felt we were just focused on the low Earth orbit aspects of the station. They also, you might refer this as the sticks and balls, or they called it 5 meters truss. So almost 15-foot squares on those segments, and they would put them together, and they came back and evaluated again and said, okay, there's still too much EVA necessary to assemble station. So that really kicked off what we really are today, which was called pre-integrated trusses. The shuttle was a great workhorse for us. It was very convenient for the U.S. because we had the shuttle. Shuttle became the primary transportation mode to bring all those elements up to space station. There was over 37 shuttle missions just delivering cargo, elements, crew, food, services, supplies to station from 1998 through 2011. So it was very much of a workhorse. And the pre-integrated aspect allowed us to build a module completely intact with an interface on both ends that would attach to a next module as we built out from the center. And they thought they'd have to move all these modules around. We have these air bearings, floors, and slide them together, make sure they'd fit before we'd launch. Quickly, NASA said, well, you know, that's going to take too much time, too. In fact, all of us from Houston here, the Sonny Carter test facility, which actually was built by McDonnell Douglas, who ran Work Package 1, which was the trusses. They were going to assemble all their elements there. You could fly into Ellington Field, you'd roll them out into that big warehouse. At one time, it was all one level, and we'd be able to put all these units together. We'd do integrated testing together, and then we'd take and barge it from down the street to Clear Lake, and then barge it all the way over to Kennedy, and then launch it. That was the concept. And in about 91, NASA asked Boeing to get involved in this as an integration contractor for station. And Boeing builds big airplanes, and so they said, well, we don't have to have all our fuselages touch each other before we do our final assembly. We know how to use tooling, and we know how to do digital pre-assembly of measuring things. So the whole station went to a new concept that was pretty amazing, so that when you eventually got up there, you'd never touched the other element before, and we had 100% success on all interfaces, hookups, power, transmission, data, communications. It was really a marvel, and a lot of that goes back to the requirements NASA wrote, very intelligent on how to make sure the systems are checked out, how to test things, and the response from the contractors. It was a large community of contractors. Work Package 1, as I mentioned, was McDonnell Douglas. It was actually out of Huntington Beach, the location for the contract, and it was Johnson Space Flight Center. They owned Work Package 1, and they were building the trusses with McDonnell Douglas. Work Package 2 was the pressurized elements. That went to Marshall Space Flight Center, and Marshall Space Flight Center worked with the Boeing Huntsville office to build those modules, and it did a very good integration job and all the ECLIS systems, and that's why you kind of have that hub in Marshall, both on pressurized elements, environmental life and support systems, and payloads, because it was all kind of integrated there back in the early days. And then as you did the power system, the NASA Glenn, it used to be a Lewis Research Center, NASA Glenn today, but anyway, they had the Work Package 4, which was the electric power system. They selected Rocketdyne. Rocketdyne, you think of engines, but Rocketdyne also had an energy sector of their division, and they did a lot of both nuclear testing, nuclear power plant support, electrical power plants, a lot of solar array activities, and just overall power bus systems. So they won the contract for electric power, and so Rocketdyne from Southern California, where I reside, is how I kind of got introduced to space back in 1987. So this conglomerate of companies obviously also was integrated and led by Boeing. They had the prime contract, and then eventually in 96 and 97, Boeing joined with all three of those companies. All three companies joined together. So there's kind of a myriad of history of both space station, the assembly of the Boeing company, and the technology that NASA brought forth that really, to this day, has allowed us to not only operate this vehicle for the 15 years that we designed it for, actually expand it to what we're projecting that we could easily last for 30 years. And in fact, we have stress engineers today that are working well into 42 years and seeing what else they could do to take and add some more life. I mentioned a little bit about the Russians. Well, President Reagan said it's going to be an international space station. About 91, we also know that the Soviet Union collapsed. And at that time, the U.S. was very concerned about all the technology that the Russians had and how we could work together to make sure we protected that technology and it wasn't used for weapons or for efforts against the United States. So it was now President Clinton, and with his advisors, with NASA, they determined that we could join with the Russians and be a member of this multi-agency consortium building this International Space Station by now. And it worked very well, as you know. That picture over my left shoulder is actually the Mir space station. So Soviet Union falls, the Mir space station is already up in space. It's been there since '84. And so there's crew up there, and need for resupply, need for safe return. They were very worried. So this joining with helping NASA on International Space Station actually helped the Russian states continue to operate Mir station for about 5 more years, about 97, 98. And the timing was perfect as Mir came down, International Space Station, first elements were built and launched. I put this up because when you think about space station, you may not realize, but about 80% of it is U.S. contributions, and that's all in the blue as shown there. Space station weighs almost 1 million pounds. It did weigh over 1 million pounds when the shuttle was docked with it. The shuttle is about 250,000 pounds. So we're somewhere upwards about 900,000. It's truly amazing, and so the blue are all the truss elements, the pressurized modules. And down here on the green is the Columbus module, the European lab. The burgundy is the Japanese module and logistics module. And then the red at the very top are the Russian modules. And so if you really think about it, when we talk about science, there's really 4 science laboratories on space station. You have the U.S. lab. You have several efforts in multiple Russian elements that are laboratory-like. And they're launching a new lab probably a year from now to add another appendage to their side of the station. You have the Columbus module, which is European, and you have the JAXA module for GEM. So lots of opportunities for science. Scott's going to go into a little more detail on some of the things that go on there. I think you'll enjoy the aspects from the science perspective. So in last November, we got to celebrate 20 years. So it's 20 years since these 2 elements first went up. November 20th, the Russians launched their, in 1998, the FGB, as we call it. It's a major configuration block where the computers and main controls are for their vehicle. It also has propulsion in it. The U.S. Launched in the shuttle the Node 1 that has those 2 kind of canted black tunnels that allow the node, which has multi-ports, 4 radial, 2 axial, to join and be a building block for other elements. That was first mated, so built 7,000, maybe 7,500 miles away, one in Moscow and the other one in Marshall Space Flight Center. And launched in different parts of the world, Baikonur and Kennedy Space Center, first met up in low Earth orbit, flawless docking operation, and then hatch opening. And as you know, the crew, with lots of stories back in December and November here of all the excitement for these first elements. That has been 20 years. It's truly amazing. Pretty exciting. But that didn't just happen. You know, we built station in segments. It was very planned, very well orchestrated. From the early elements that even on the previous page, the upper page left there is the Russian module, and then we'll keep building it. The upper right is the power module where we were able to get about a 30 kilowatt power module up to station so we could start allowing the crew to live on board and remain on board. And that's why, you know, we have, if you're an 18-year-old today, you've never known a time that there hasn't been someone living in space. Because in November of 2000, just 2 years later after starting initially building this, we now have a crew of 3 living on board space station. So you went from the early setup to modules, build up a few more modules. You have a power module on there that's generating about 30 kilowatts of power, which is probably more than you use any one day in your house, probably about 2 houses worth. And then they're building up, and now they're doing science, and they're doing crew activities to sustain life in space. Pretty amazing. And now 18 years, if you're only 18 years old, you've probably never known a time when there hasn't been someone living in space. In fact, you've never known a time that there hasn't been a space station. So we started to get symmetry. It's very important when you're in space. Space does have drag as you're flying along there. You don't think there's no gravity, but there is drag. So as you are orbiting Earth at 17,500 miles an hour, you do tend to fall back to the gravity zone towards Earth. So that's why your propulsion modules keep you afloat, keep you the right separation from Earth's re-entry. You want to minimize your drag in your vehicle. So we have a nice symmetric mass in the middle type structure, which is very stable. Kind of even the Mir station was very similar. All the mass was off of one joint. We have 2 power modules. Now you're starting to get redundancy on your power modules. So now we're up to 60 or so kilowatts. You can see we got more pressurized modules. The lab's up there. You have probably node 2 is also up there. The Russians have extended their side of it. And so you're really building up capability. And you take it in increments because you have to launch, you have to build these things, you have to test them, you have to launch them. So getting them there safely, it doesn't happen overnight. And there's always anomalies that happen. Obviously, between the upper right and the lower left, we did have the Columbia accident. So we were down about 2.5 years of launching. We didn't know if we were going to finish this. We thought maybe we could be stuck on the one configuration for a U.S. space station or an international space station. And due to the return to flight and all the due diligence that NASA and all the contractors put into flying shuttle safely again, we were able to continue building and eventually get to the full symmetry of 8 power modules that are generating more than 120 kilowatts. If you think about a neighborhood, let's say one of you lives in a cul-de-sac, less than 10 homes, kind of this power station could feed your neighborhood for all your demand you'd ever need 24/7, 365. It's enough power to keep that much of your activities, your air conditioners, your dishwashers, your computers, your TVs, heaters, everything going safely, effectively. The pressurized modules are about the volume of a 747. If you think about flying internationally, a big airplane, you're walking along, think about walking through that 747 from front to back. That's what your pressurized module volume would be. It's about equal to a 5-bedroom home. And so it's a big, I won't say palatial, but it's a big, that's why we can afford to have 6 crew members or more visiting as we pick up. So there's lots of activities that we can do. Scott will go into some of the things inside. It took about 200 launches to date. So if you think about building it, both shuttle the Russian launch vehicles. We had the European launch vehicles bringing up logistics supplies. We have the Japanese HTV bringing up logistics supplies. And we have commercial crew, SpaceX and Northrop Grumman bringing up supplies today. Add them all together to date, 20 years of this operation, we've had about 200. If you think about as NASA generates a commercial market in space, they have added capability and in launch, which is greater for all the satellites and other launch providers to compete for price to get to orbit. So big benefits on that. The old Mir space station, this is about 4 times the volume. Skylab, if you're a little bit older, you remember Skylab? This is about 5 times the volume of Skylab. When they found some of these audits and said, well, it's going to take too many EVAs to build space station, you can't do it that way, we're going to do it this way. It's still, we've still had 212 EVAs to assemble, maintain space station from original elements to today. So lots going on, lots of things, but it's pretty amazing. So we always ask crew members, what's the first thing you do when you get to orbit? And pretty much unanimously, within the first couple of hours, they've run to the cupola, they gaze outside the windows and look at Earth. Start to recognize points of interest they've either been, or maybe if they're luckily they're going over the United States or Russia, whatever their homeland is, and they recognize points across as they're going by. It's truly an amazing opportunity to view the Earth, and Earth science is truly amazing opportunity. We're also looking at growth opportunities. In the lower little inlet there, that's the airlock. Right now we're looking at adding an airlock that will allow customers to bring up payloads that either want to be launched from space station or maybe assembled and exposed to radiation or sun, or exposed to the vacuum of space or sensors. And what you can do is you can build it up. The crew on orbit could build it into that little round little cubicle, another looks like a cupola is what I meant to say. And then what we do is we unbolt it and we pick it up with the arm and we expose it to space. You could launch little small sats from it. So it's really looking like a new opportunity of business. So it is a commercially provided element. It's going to be launched and assembled to station and allow additional access. So station built with a dream certainly has had a long venue of getting built, going through requirements, certification, testing. It had a very distinguished assembly of flawless matings and power turn-ons and safety for the crew. We're into life extension of ISS as we look for the next 10 years. We're talking with Congress, both House and Senate, to see what the appropriations could be for ISS to continue longer than 2024 as the President's budget indicated. And we feel very strong that we'll have a lot of opportunities well ahead of us for another 10 years. So we're going to continue with our life extension to make sure we do what's right. So with that, I'd like to invite Scott up. Is that it? Yep, that's it. All right, thank you, Scott.
Thank you, Mark. Yeah, I'm always amazed when I sit back and think about the engineering achievement that it took to pull the space station, get it built, and then operate it flawlessly. The scientific community is so fortunate to have such a unique laboratory. It's the only one in the world. I'm happy to say that with the 15 nations that built the station, well, the story doesn't end there. So we are certainly seeing an increase in payloads that are coming to the station, and particularly over the last 2 years. There's a lot more commercial payloads than we've ever seen in the past, and we hope this will continue, and the trend looks like it will. As Mark said, we've been fortunate to conduct experiments on the board, the space station, ever since the manned crew started in November of 2000. So for the last 18 years, experiments have been going on, and trying to look back through the last 18 years and come up with some highlights is a very difficult challenge the last couple of days. So these, the ones I'll be talking about tonight are some that I think would be of interest. So thank you very much for coming out tonight. I know it's cold, but I hope this will be informative for you. This next chart's an eye chart, so I just want to point out a couple of items on here. So at any given time over a 6-month period, there's about 300 investigations that are taking place. So from the start in November of 2000, we performed over 2,600 investigations, and those represent inputs from about 3,000 different scientists from around the world. So I like to think of it as you have your immediate family that built the space station, represented by the 15 nations, but you've got 130 in your extended family that are actually using it from that many countries. So very unique. We're very fortunate to have it. There's been a lot of publications that have come out from station, over 1,600 publications in peer-reviewed scientific journals to date. In the lower left-hand side of the chart, you'll see a bar graph. Those just represent, over that 6-month period, the distribution of which partners, the 5 primary partners, were doing the science. And the lower right shows the distribution between what we call the National Lab and the NASA payloads. So everyone wants to know, what's it look like inside the station? So here's a good picture, and it just happens to be Jim Voss, who's a graduate from Auburn. I should have found a picture with him wearing an Auburn shirt, but so all the experiments typically in the pressurized area are put into the racks. So the floor, ceiling, all 4 sides are covered in racks. Those house our subsystems, but they also have unique payload accommodations there. We have dedicated facilities on board to do research. We have dedicated areas for fluid experiments, combustion experiments, human research, life sciences. Mark had mentioned Earth observations. We have glove boxes that can handle toxic materials. That's for both material science and for life sciences. And then we have common equipment like you would find in any Earth laboratory, particularly for the life sciences, which involves refrigeration and freezers. The racks provide our power. They have data interfaces. We have active cooling. And then we have availability to have vacuums and gases supplied to the payloads. So external to the station, this is a picture of an external platform. There's 8 or 9 platforms at various locations on the outside of the station. They have different viewing areas, so you can imagine if you have a payload that needs to look into deep space, some of those spots are prime real estate. Other ones have unique capability to view at the Earth. So there's usually a wait list for these positions. In this particular picture is a material science experiment that Boeing was involved with the Air Force Research Lab. It's called the MISSY experiment. And we were looking at different materials and looking at their optical properties and how they would hold up in the space atmosphere as it's exposed to atomic oxygen and such.
Go for main engines. Space shuttle Endeavour.
Becoming an astronaut was like you were walking in the clouds when you first found out that you'd been selected. My first space flight was on the Space Shuttle Endeavour, STS-113.
Rolling onto the proper alignment for its 8.5-minute ride to orbit, 4.5 million pounds of hardware and humans taking aim on the International Outpost. The Expedition 6 crew, Kent Bowersox, Nikolai Budarin, and Don Pettit seated down on the middeck headed for their new home in space.
Looking at Earth from space is amazingly beautiful. It's a perspective where you can see things on the length scale of half a continent. apart from everything else an astronaut does on orbit, photography is actually part of our job.
I'm going to set up to do atmospheric air glow images.
We take pictures of Earth and the surroundings of Earth, the upper atmosphere.
Manually, you got to manually do the f-stop, you got to manually do the focus, and now you got to look through this thing.
These pictures in themselves represent a scientific data set recorded over now for 14 years. Astronaut imagery of Earth is an example of learning what you need to take pictures of and how to take the pictures. Space is a place where your normal intuition does not apply. Things don't work the way they do down here on Earth. You are moving at 8 kilometers a second. That's fast. And so you have to be able to slew the camera at the same rate of orbital motion while you're taking pictures to actually get the sharpest imagery. My favorite subject is the Earth at night. Aurora is just amazingly beautiful, and it's this glowing upper part of the atmosphere that crawls around like amoebas in the sky. And then cities at night, the way human beings sprinkle their light bulbs around. It's a fascinating statement on how we as human beings define our urban areas. In terms of the star trail pictures, the stars are moving because of the pitch axis of station. The cities move by because of your orbital motion and Earth's rotation. There's all kinds of other delightful physics and natural phenomenon that you can see in these pictures, and we can tickle our imagination and enrich our minds from this gain in knowledge. When you explore a frontier, the people who explore bring back images and bring back stories about what these frontiers are like. I feel an obligation to share this experience so that everybody else can at least participate through the eyes of the people who do go into the frontiers. I'm Don Pettit. I'm a photographer and an astronaut.
It's just amazing some of the views that come from the cupola window. So I wanted to share that so you could have a perspective of the type of observations that the crew can do when they perform their experiments in that area. We also have a window in the U.S. laboratory that Mark talked about. That's very utilized as well. But you can imagine the crew likes to spend a lot of time in the cupola with that 360-degree bay window. So a lot of people want to know, why do we do science in space? Well, so what's so unique about that? So I thought a good way to do it, if you look here on the left-hand side of the screen, you can see what boiling water would look like on the ground. Everyone's boiled water on their stove. So, but in orbit, you don't have buoyancy-driven convection. So as the water boils, it just forms one big bubble. So that's a good way to visualize it. On the other side of the screen, you'll see what a flame would look like. It burns in a very spherical order versus with no convection driving the candle upwards. So that's why we do. Things work differently in space. And when we were building the space station, everything would work very well on the ground, but there was always surprises. When you go to orbit, things just don't work the same way. And that applies to biological systems as well. So there's changes that take place. We have issues with biofilms in our subsystems that we have to deal with. The biological systems change, genes turn on and turn off depending on what it's exposed to. But you can design an experiment to take advantage of that and have some insight into the actual processes that are taking place. One of the big areas of research has been in the area of crystal growth. Crystals in space grow slower, and you can grow them much larger. So you can get much higher quality of crystals. So on the left-hand side, this particular crystal, you can see what it looks like grown on the ground versus in space. You bring the crystals back to Earth and you can do X-ray diffraction or neutron diffraction, and from that you can determine the three-dimensional structure of the molecules. So there's many people doing research in this area, a couple of pharmaceutical companies. Tahoe Pharmaceutical has been doing some clinical trials on a new drug for treating Duchenne's muscular dystrophy. The Merck Pharmaceutical is also looking to improve a formulation for one of their cancer immunotherapy drugs. Oak Ridge National Laboratories, they've developed an improved antidote for nerve agents and pesticide poisoning. The Michael J. Fox Foundation, which most of you are familiar with, they're doing research in this area to look up the causes of Parkinson's and countermeasures for that. And then finally, the researchers at Illinois Institute of Technology, they're looking at using crystals for enhanced radiation monitoring devices. Another big area is remote sensing. Here's a picture. We have capability on those external platform sites to place instruments. This one happens to be a hyperspectral image that was done several years ago, and it's looking down at the Pensacola Bay. And the object of this was to look at water quality in the coastal regions. So chlorophyll, which is a sign of algae, is an indicator that nitrogen is flowing into the bay, and typically that would be coming from agricultural areas with fertilizers. So that's an important marker for water quality issues. The high areas of chlorophyll are indicated in the yellow and the red. That shows that algae blooms are present. There's other uses of remote sensing as well. You can look at agricultural crop conditions, natural disaster management, and locating minerals. We have a pointing system that a commercial entity has placed on board the space station called MUSES. So it will house multiple instruments and allow you to point at different locations. Also in the area of astrophysics, this particular experiment is called NICER. It stands for the Neutron Star Interior Composition Explorer, which is a mouthful. But it's looking at neutron stars, or what's called pulsars. Pulsars were first discovered in 1967. There's been 2 Nobel Prize awardees in doing research in that area. These are the densest objects in the universe that we're aware of. So they're very small, only about 20 kilometers in diameter. So it's about the size of New York City, or about from here halfway to Hobby Airport. But if you took 1 tablespoon of the material, it would weigh 1 billion tons. So it's very, very dense, very high gravity, and it spins approximately 36,000 RPM. So certainly doing research on that is impossible to do in a lab here on the ground. So there's been they've been probably the most publicized experiment to date. Just last week, Nature Journal put it on the cover of their latest journal for the January 9th edition. One of the things that they did about a year ago, they were looking at pulsars and trying to figure out if you could use the blinking as a beacon for interstellar flight. So they were just back like in the Columbus days, using your sextant at sea. They did a similar experiment and showed that they could navigate using pulsars as beacons. The next one I want to highlight was an experiment that was done looking at the salmonella and how you could take advantage of the changes that occur molecular to make it more virulent, how you could use that as a potential way to design a drug to come up eventually with a vaccine. So Dr. Cheryl Nicholson, she's at Arizona State University, did the research, and she's used this unique laboratory in her quest to develop a vaccine. So you'll hear from her directly here.
The International Space Station's National Lab is a unique testbed for research in the areas of biology, biotechnology, physical and materials sciences, as well as Earth and space sciences. ISS research has resulted in major scientific breakthroughs and real benefits to humanity.
We're learning something new about how disease is happening that we can't learn down here with the force of gravity. What my team works with, it's the leading cause of death of young adults and children worldwide, kills 35% of people globally. In the United States alone, it's a huge problem for us here economically.
Salmonella is one of the leading causes of foodborne illness in the U.S. and is the #1 cause of death from foodborne illness.
My team showed that culturing pathogens in the unique environment of microgravity opens up new windows in terms of how they're causing disease in our body that we can't see when we grow them down here conventionally.
In microgravity, the Salmonella pathogen has shown an increase in virulence or an increased ability to cause disease.
Microgravity is an extreme environment. And every time, as scientists, we have pushed living organisms, cells, organisms themselves, to grow, to thrive, to live in extreme environments. We've learned enormous things about how life survives under these conditions, and what's even more, we've been able to take these novel insights for how these cells are behaving to extreme environments and translate them into products that we use on a daily basis. The general public of America needs to understand the value to them to solve major challenges of human health and quality of life, not just for this country, globally.
Okay, the next one I want to highlight is an experiment that I thought was very unique. It demonstrates a partnership between two very different industries. So the European Space Agency partnered with Norway with their emergency management team that deals with shipping. And so if you look there on the bottom of the screen, just like we have air traffic control systems, there are transmitters on each of the ships that are out. But the issue is they can only see or be able to be tracked about 75 miles from the coast. So once you go past that point, the curvature of the Earth, you won't be able to get the signal. So the unique thing, though, is the radio signal's still there. You just can't receive it on the ground. But what's flying overhead at 250 miles is the space station. So ESA placed a receiver on the side of their module that's seen in the upper left. And they were able then, they turned it on, and that was in June of 2010. And so the description they gave us, it was like a blind man beginning to see. All of a sudden, they were able to track 30,000 ships a day with that. And it really came an important milestone for them to justify that work. Really showed up 2 years later in January of 2012. There was a ship called the Hallgrimmer fishing vessel. It had capsized. One individual ended up being the sole survivor. They were able to use the data from the International Space Station to find ships in the vicinity of there in the North Sea, which is a very difficult place to try to survive. And they located one person. So they were able to reach him within 3 hours using the data from the space station. So that was a pretty unique use of the station. The next one, a lot of research that has a lot of benefit for those here on Earth is research in the osteoporosis. So Amgen, Mark mentioned all the different flights it took to build the station. This is one of the experiments that we were able to do during the assembly process, very early on the assembly. So we were able to fly some mice to the station. They were looking at trying to develop drugs and test the drugs' effectiveness. What we found that in space, you lose or reabsorb your bone loss much faster than on the ground. And here on the ground, a postmenopausal female can experience 1 to 1.5% hip bone loss per year. But in space, the astronauts can experience that in 1 month. So it's very accelerated. So Amgen wanted to take advantage of that acceleration and be able to fly the mice and be able to get a lot of results without waiting a lot of time by trading them. So osteoporosis impacts 44 million people in the U.S. alone that are ages 50 and plus. And with the data, they were able to bring 2 products to market, drugs, Prolia and Xgeva. Xgeva was, I believe, actually tested with the mice. Some had been treated with it. And so that one was already on the market. Then Prolia followed shortly thereafter. So that was an example of rodent research. And we have a huge amount of research going on, and it's continuing with rodents. We've done 9 missions to date doing rodent investigations. We've looked at immune systems, wound healing, visual acuity, and muscle atrophy. This next example is how we took the technology from the Canada arm, that was the robotic system, and we're able to, McDonald Detweiler out of Canada that designed the robotic arm, and Dr. Sutherland from the University of Calgary. They were able to combine resources and take that technology and put it to use in the operating room. So as most of you have all had MRIs or know someone that's had an MRI, you cannot put any metallic items into an MRI machine. So they were able to use the same materials that were used on the space station, use a lot of the software particularly that gave it the dexterity that a surgeon needs to do surgery, and combine that into a robot that would allow surgery while you're inside the MRI, getting real-time visual cues from that. Dr. Sutherland stated that the resolution of this robot, they call it a neuroarm, is much, much better than the finest surgeon in the world. So the first patient that underwent brain surgery was Paige Nicholson in 2008. She had multiple brain tumors from neurofibromatosis, and commonly referred as the elephant man's disease. But sometimes the tumors grow on the outside, sometimes they grow on the inside. So with hers, they were growing in the nerves of her brain. Very delicate, very difficult surgery, and they were able to accomplish it using the neuroarm for the first time. I mentioned that we have facilities for doing combustion experiments on board. In this picture, you can see an example from the flammability and extension payload. We call it FLEX. The picture on the left shows an initial N-heptane fuel droplet. It's about 2 to 3 millimeters spherical droplet. It's burning at a temperature of about 2200, 2300 degrees Fahrenheit with this blue spherical shape. The picture on the right of the screen will show a second combustion that's taking place about 20 seconds after the initial combustion stopped. So the researchers at the Operations Control Center saw a very peculiar orange afterglow. No one really understood that. So additional experiments were done. That's one of the items that's really unique about the space station. Back in the Space Lab days and such, if you saw something, it would take you 2 to 3 years before you could refly your experiment again to further investigate. With the space station, it's a very flexible platform, able to repeat the experiments. So they kept looking at that, and it turns out that this secondary burning is taking place at a much lower temperature. It's only 400 to 1,000 degrees Fahrenheit. And it's got a very different chemistry that's taking place, so they call it cool flames. But trying to understand that combustion process will allow you to maybe develop more efficient engines and fuels that are more efficient and less harmful to the environment. There's other areas of research with combustion that's taking place on station. Inside the microgravity glove box, there's Mulqueen, which is a large manufacturer of chemicals and textiles. They're looking at different fabrics and how they burn in space and how that could help them design new clothing for firefighters and the military to help protect them from second and third degree burns. Sapphire is another unique experiment. It's not actually performed on the station, but it's done inside the visiting vehicle, the Cygnus, once it departs station. They intentionally set a fire inside a contained box, keep it burning, and look at that process as it re-enters, and the entire Cygnus burns up during re-entry anyway. But they have video that comes in and data from that, and that's going to help us in the design of our next generation spacecraft. This particular experiment here is an applied research experiment. It's looking at surface wetting. So Eli Lilly was very interested in the process by which tablets dissolve. So here in the middle you'll see a tablet, and then it's got this gel around it. So it's very critical when you have medication, when you take the tablet, to get the proper dose of medicine. So they're looking at this to optimize their processes and understand exactly what's taking place in that process. There's other experiments that are similar, colloid experiments. So a colloid is a solution that has particles that are very small, 1 to 1,000 nanometers in diameter, yet they're able to remain evenly distributed throughout the liquid. Things we use every day that you wouldn't realize would be a colloid would be your toothpaste, a lot of your cosmetics, your whipped cream, your milk, your butter, your jelly, all those are colloids. So there's a lot of research going on in that, and those are usually done inside the glove box, and sometimes they're done out in the cabin itself. With and most of the data you're getting from that is just video-based. So the next one is a short video looking at a model for cancer therapy. Boeing and the National Lab partnered to sponsor this particular payload. It's called AngieX. And they're looking at targeted vascular therapeutics to get rid of cancer. But there's a real challenge when you're dealing with the blood vessels in the body. Endothelial cells are the cells that line your blood vessels. And it's very hard to find a model organism on the ground that can mimic what's going to be happening in your body. So they're doing a study. It launched in June of 2018. We don't have the results back yet, but they have a hypothesis that the endothelial cells that could be grown on the space station could become the model organism you use. And that's a challenge for any drug company that's trying to has a challenge of trying to do drugs to attack the vascular systems. So here's a short video of that.
We're trying to make a therapy that can address 90% of cancers and make cancer a non-fatal disease. In the U.S., over 1/3 of people go on to develop cancer in their lifetime. My mother died of cancer, and she died at age 33 when I was 10 years old. Wasn't able to do anything for her when she was alive, but I can at least have made my contribution to all the future mothers who might be in a similar situation.
Microgravity is providing a very good model for us to study how drugs are targeting normal blood vessels and to test our cancer therapy in this model.
Our approach destroys both the tumor cells and the tumor blood vessels simultaneously, and the whole tumor dies for lack of oxygen and nutrients. We notice astronauts have more cardiovascular disease but less cancer And we noticed endothelial cells, which are the type of cells that make up blood vessels, didn't grow in space. So we're sending up a bunch of endothelial cells. We're going to treat them with our drug. And we want to see if endothelial cells in space are different than on the ground.
NGX's mission is to cure cancer, and microgravity may provide that opportunity.
Okay, my next example then is looking at a company called Lambda Vision. It's also a payload that National Lab and Boeing are sponsoring. And they're looking at manufacturing in space a retinal implant. So they think the quality that they can manufacture in the zero gravity environment will be much better than what can be done on the ground. So this experiment's on orbit now. We have not received the results back yet, but there's a lot of hope for this. There's also other exciting areas of doing manufacturing in space. There's research going on for 3D printing. Several companies are looking into that. Fiber optic manufacturing. We can get improved fiber optics. There's already been one demonstration of that, and coming up very soon is going to be another manufacturing round of that. Then one of the really big, exciting ones that I think of that's a future payload that will be flown sometime this year is a biofabricator, where it's going to be able to print a heart patch. And eventually, their goal is to be able to print organs, full organs. So that's being done as we speak. So on the ground, they're doing them, but there's challenges with doing it on the ground because the 3D structure tends to collapse. So doing it in space, you don't have to deal with the gravity. They think there's a market there for this type of manufacturing. That should be really unique. Okay, the next slide I want to talk just briefly, molecular biology. I've been fortunate that I've been somewhat engaged in this area. Certainly not a scientist, I'm an engineer, but 2016 was a big year for molecular biology. Polymerase chain reaction, or PCR, we flew the first one to the station in April of 2016. We actually did this as part of a STEM education program that we'll talk about here in a moment. But if you think of a PCR, you have your long piece of DNA. You could think of that as being a set of encyclopedias. But maybe the part you're interested in is only one sentence out of that whole volume of encyclopedias. So a PCR machine is a way to go in and target that one area you're looking for, and then you make 1 billion copies of it. So it's a little thermal cycler that will allow you to make just like a Xerox machine. It will produce 30 billion copies, or 1 billion copies with 30 cycles. Little later on that month, Dr. Sarah Wallace here from JSC, she also flew a unique device for the first time. And this was called it's a gene sequencing device. Usually these are quite large. They would fill up a full lab bench in your lab on the ground. But the one that she flew is this one right here, one just like this. Very small, compact. Both of these technologies are really game changers. But when you put them together, it's very powerful. So this is the first time in 2016 that they've been able to do molecular biology experiments on board the station. So routinely we have to bring samples back of swab samples for bacteria and water samples. In the future, we're testing protocols now where we'll be able to do all that on board without bringing all these samples back. So it's really a game changer in that area. So the next slide I want to talk about is a flagship program for Boeing. We call it Genes in Space. It's a STEM education. There's a lot of STEM education activities that's going on the station. And it's reaching thousands of young men and women throughout the U.S. and the world. So we're very fortunate to just be one of those. So the Genes in Space program, we target students that are grades 7 through 12. And it's a DNA experiment that uses the PCR and the sequencing that we just spoke about. But they have to design an experiment that would solve some problem that's space-related. And it has to require the microgravity environment of space to do that. So we're in our 5th year of the competition. Last Monday, we opened entries so students can start submitting those. It's a very unique program. Our partners, we're partnered with several other companies on this. We have Mini PCR, which is our primary, they're co-founders with us. We have New England Biolabs, Math for America, and the Center for Advancement of Science and Space are also our partners. It's been very promising, the results in the science they're doing. We've had 2 journal articles already published from the first 4 entries, and we've got 2 more in evaluation right now. So it's really cutting edge. So let me show you a short video of our Genes in Space 2 winner.
Minus 30 seconds.
28.
3, 2, go for main engine start. 1, 0, and liftoff of the Atlas V rocket with Cygnus.
What I've been focused on, for the past year or so is really a very specific genetic change that can occur in astronauts when they go to space.
I couldn't imagine any individual being more impressive than what Julian is. What he's already done as a young student through his high school career and now moving on to college, the sky's the limit for Julian, there's just no doubt about it.
It's truly a very immediately relevant experiment. If we want to travel deeper into space, if we want to have longer term missions, assessing the health of astronauts every step of the way becomes crucial, and doing it by directly measuring the health of their chromosomes is a great way of achieving that.
The deal with telomeres is that they protect the tips of our chromosomes from damage, but as we get older, they get naturally shorter.
Well, that's the thing I found. When you go to space, the body changes, many things change.
D180 continues to perform well.
This is another reaffirmation that there's a lot of talent out there. There are a lot of amazing kids with bright ideas, and Genes in Space is just a platform for them to bring those ideas into reality.
What Boeing has done for this in such a deeply important area, you can't say enough about it.
The STEM education is so important for us to encourage the students, young men and women, to stay interested in science, technology, engineering, and math, because they are the future of our company, for sure.
To make something that has the possibility of becoming a breakthrough, that's more than enough. So I'm so grateful for everything I've been given. Totally amazing. It's pretty special, yeah.
Next stop, International Space Station. I'm always impressed with these students. They're just brilliant. We were very fortunate that last week we had last year's winner coming here, and then we did a boot camp with them basically to go over their experiment. And of course, we have to optimize it to get it ready for flight. And it's going to be flying up on the next SpaceX flight in March. So they came and did a lunch and learn at Boeing, and it was so well received. They're just amazing individuals. So there's a lot of other partnerships. I mentioned that the commercial...
Minus 30 seconds.
A lot of other partnerships that are taking place in the commercial entities out there. I want to mention a couple of these. These are companies that we typically haven't seen as doing research on station until recently. So Target. You might wonder why in the world would Target want to do research on the space station. But they're very interested in cotton sustainability. So they put together a challenge. It turns out that 25 million tons of cotton per year are produced globally. And that has significant environmental impacts. 1 kilogram of cotton requires thousands of liters of water to produce. So they've put a challenge out for ideas on how to improve that. So that's ongoing now. Goodyear Aerospace, or Goodyear, they have a materials science experiment, as you can imagine, based on the name of the company. They're looking at trying to improve tires, and so silica particles, so they're doing studies on that. That's also going to be flying later this year. Very unusual one here is Delta faucets. So as most of you know, your bathrooms and your showers, you have all these low flow fixtures now. So that wasn't an issue a few years ago, but the pressure and the supply of your water has, the flow rates have decreased. So they're doing a lot of studies on droplet formation studies. They want you to be able to understand how the droplet is formed, and they're using microfluidics for that. It's really governed by your gravity on the ground, your water flow, and the pressure. So if they can eliminate the gravity, then they only have two variables to play with to try to understand. So their goal is to use less water in your faucets, but make you still have the same sensation of the wetness as you take your shower. So that one's really unique. Anyone here have an Apple TV? So Apple TV flew a 4K high definition camera to the station. And so last fall, they released their new aerials with a lot of footage that was obtained on the International Space Station. This incentive, they announced it at their July 2018 announcement at the Worldwide Development Conference for Apple. So that's kind of a unique. If you haven't seen those videos, if you have an Apple TV, make sure you pull it up and take a look. Then you have a couple of pharmaceutical companies that you wouldn't be surprised. Those Eli Lilly has 5 experiments going on right now for drug development. AstraZeneca also has some proprietary drug development studies going on. But the one that really probably jumps out at you is Budweiser. All right, so in March of 2017, Budweiser announced publicly, and they did a PR release, that they want to be the first beer on Mars. So I wasn't aware of that till I started doing a little homework on it. But they've flown 3 experiments to date, and they're going to continue to do some more. And what they're looking at, they want to be in a position that they can have a product available when that time comes. But the benefit to Earth is, as they understand how the malting process better, and the rapid hydration and the germination and the drying that's involved in that process, they want to be able to improve their product and the shelf life for when it's exposed to a stress environment such as heat and storage and transportation. So it's kind of a dual-fold incentive there, but I thought that one was pretty unique that I would share with you tonight for that. So Station is a very unique platform, and one of the big items that it can be used for is a test bed for our exploration. So we've already seen advanced life support systems being used there as a test bed, improved waste systems. We're growing plants on stations to be a food source for the future, and they're doing laser communication technical demonstrations. So there's a lot of benefits for when you're trying to get ready for the next generation of products coming forward. So I'll close with that. We have a short video, a little summary, no audio, it's just a video, but it's some good footage here.
Wow, that was a lot of information. That was really fascinating. We're going to have a little time for some questions. I'm going to bring the panelists up here, and I'm going to transition over here to this chair. We have our microphones. I think this is something I can maybe share with all of you that I think is actually pretty cool. So we are actually talking to having the beer premiere here this summer. And there's actually some barley that's been taken to the International Space Station. It's going to be called Discovery Brew. So you get to taste it here for the first time at Space Center Houston as part of our Apollo 15
What's the date on
anniversary.
that one? This summer, you said.
Well, I thought it was actually fascinating. I mean, we all hear about the benefits of research that's taking place in the International Space Station. I think you touched on many, but there's so much that is going on. But I'm kind of curious about this module that's going up with the Russians. I didn't realize another module is going to be added. And do you know more about what their plans are with that module? What the kind of experiments will take place on it?
Oh, I don't know the experiments that the Russians will run on it. Probably more similar to what we're doing on our side, but it's similar in size to their current modules. It'll be a big proton launch, bringing it up, and it's probably towards the end of this calendar year. That's the expectation. It's been delayed several times, so it's a research module, and it's going to help expand their racks and their studies and what they have planned for their science and for their country.
So how many more nodes could be added to International Space Station beyond this new one that's going up?
Funny you should ask. So certainly there's opportunities for a commercial module to come up to the U.S. side. That's something that we're looking at in the future. That's a NASA decision that's still being decided up in headquarters, and certainly something that could probably be announced later this year. But that would entice a commercial company to want to put their module, design it, build it, test it, and then launch it to station, and we'd integrate it up there and allow them to do additional science, expand the capabilities we have already.
Fascinating. Well, one thing I've heard about is because the original design of the space station actually dates back decades, right? And so you look at how information technology has advanced. What about the infrastructure on station? Can it sustain this new technology, these new things that we're adding?
Yeah. So a couple of examples. So all of us probably have high-speed internet at home. You just take for granted your downlinking of movies and what have you. Space station, of course, was built in the 90s, even though we launched in 2000s timeframe, but it was built in the 90s. Some of it was even designed from technologies in the late 80s. So when we were downlinking speeds of 300 megabytes, that was top-notch. And just recently on orbit, we've doubled that downlink speed up and down to 600 megabytes. Yeah, it's like doubling the volume of your internet speed. So not state-of-the-art, certainly, but we have a lot of protection to make sure that we don't have people tunneling in, viruses, other things. Plus, we're going through satellites, TDRS, to downlink to ground stations. So there's a lot more complexity than what we have here on the ground. But so upgrading systems, so doubling our speed for uplinks and downlinks. There's 52 computers on space station. But don't get excited. It's not like you have gigabytes of data storage. I think there's only less than 2 gigabytes of data storage on it. So we use it wisely. But we have about 2 million lines of code on space station that we operates all the systems. It integrates all the sensors. It gives us the data that we need to see the health of our systems. So we just last week we upgraded to a latest revision of software. It went flawlessly. A great job by all the teams involved. Of course, we tested it on the ground. We do quite a bit of testing on the ground. We're over in Sunny Carter in the SDEL labs over there. And we uplinked it and it went flawlessly. And all the systems that it touches were all tested to make sure that they operate and everything went very well. So we're always looking to upgrade things and provide more tools. All the companies Scott gets to visit about doing research, sometimes they need this little widget. They need something different. They need a glove box. They need a different incubator. And so we're looking to how to supplement ISS to allow those interested researchers to come up and do what they need to do. ISS has got 20 years behind it, shall we say, but we see 15 years ahead of us at least. And so power is a big deal. I mean, as you get, solar rays get old, they get damaged, they get darker, the glass starts to darken and they get less efficient. So upgrading solar rays is very important. We're looking at doing that over the next, by 2021, getting some new solar rays to help supplement the power. You know, the U.S. provides power for both the Columbus module, the Europeans, for the Jackson modules. For the Russians, we also give 12 kilowatts of power for the Russians. So there's plenty of power demands. The payloads that Scott so greatly described take about 30 kilowatts. So when you put all this together, if we can keep power going successfully, then we'll keep station being usable for all the experiments going forward. So there's lots of upgrades in mind here.
Yeah, one upgrade that comes to mind that was a big benefit to the research community, things that we take for granted at home, is wireless communication. So recently, wireless communication was put on the outside of the space station as well as internally. So a lot of researchers have taken advantage of that.
Well, something I find really fascinating is so many things have different properties in microgravity, particularly in the life sciences or biological sciences. And when you were talking about the retinal patch, the heart patch, farming organs, things of that nature, that is an incredible service. But I'm curious, how can that be upscaled? Do you have thoughts about that, or what are the discussions underway? Because it's pretty expensive to develop an organ in space and then bring it back to Earth.
Yeah, it is. I think that's certainly one of the challenges, how you turn it into a manufacturing platform. But a lot of the people that are doing manufacturing in space now are looking to, they've assumed that's probably the optimum throughput you can get, and that you tweak your processes to make those as optimized as you can. And so you'll know what your limit is on the ground. So you can use that information then to come back home and start trying to reach that same level of performance.
Let me just add to it. As ISS was really designed to be a laboratory, a specialist of science, not the high production of science or of products. Certainly, that is, as we look to commercialize space, low Earth orbit, manufacturers and companies are looking at higher production volume. That would be space with different specific technologies in mind to concentrate on, wire, or concentrate on hearts or plants or drugs. And you'll probably see that over the next 10 or 15 years, where a platform could be launched that would be a specialized manufacturing for a certain product line. And then you would visit that, either maybe it's not crew tended ever, and you just downlink suitcases of data or products, or bring resupplies up, and we'll have to figure out how to work those. But there's great ideas and great opportunities that don't all have to be fully crewed all the time. Maybe just visit it, and you put your new product suitcase in and take out the one that's completed. So there's great opportunities in the future.
So I'm curious, currently we have 3 crew on station, and because of the issue with the launch last year, but with the new vehicles that are coming online, with Boeing and SpaceX, there are 4 crew potential cabins. Is that correct, on each of those vehicles? Do you anticipate that they'll be increasing the number of astronauts on station in the coming years, and what number will that be? What will it grow to?
Well, I think there's going to be a combination of 4 through the U.S. Vehicles, 3 through the Russians. So we're already planning a sustained crew of 7. However, I think both providers have, shall we say, a 5th seat, so there may be opportunities for tourists that we have to work out. So that would make your crew a little bit higher. There's also.
Did everybody hear that? You can start saving up.
Save up, please. There's also opportunities of new modules, helping maybe supplement additional rides to do additional science. So whether 7 grows to 10 or more, the systems on ISS have to be looked at to make sure we can scrub the the CO2 and get enough supplies up there to do everything else. But we'll see what it grows to.
Fascinating. Well, we're coming close to the end of our time, and I want to at least get in one of our online questions if we have one that someone has emailed in.
Okay, here we go. All right. What are your thoughts on the concept of lunar station compared to a facility in LEO to be an assembly and jumping off point?
Well, certainly we showed, Scott at the end there showed the kind of the gateway. When you think about the lunar station, the values, first of all, the technologies and systems that we designed for LEO and ISS are certainly expandable to bring to the platform in lunar. In other words, the module technology, segment-to-segment assembly, launching, tugging systems into the proximities you want. So I think how to build the gateway, we know how to do it. I don't think that'll be a risk as far as designing, building those platforms and making them executable. The great thing about the gateway is it gives you sustained momentum for going to the lunar surface and eventually building a platform to take you to Mars. We certainly know we can go follow what we did in Apollo and go directly to the moon surface, point to point, so to speak. But it doesn't always guarantee you sustained capabilities. Just like Apollo, you could have a certain presidency that decides we're going to do something different, and then things change and you're not there from that point forward. So as a lunar platform, that gives you a lot more capability because we can go down to the surface, we can return crew samples, science back up to the platform, and then take the platform through using Orion back to Earth here to expand, study, and do other experiments. So there's such more capability in the lunar gateway that is just about to expand on with NASA. We've already had the power propulsion proposal out there, so there's companies bidding on that. There's other platforms probably coming, and there's lots of studies in that arena, so I think it'll be good.
Well, I think we could sit here and talk for hours. There are so many details, but do want to thank both Scott and Mark for joining us this evening and for your excellent remarks and expertise. Please join me in thanking them for being with us this evening. I mean, the content tonight was very rich and there was quite a bit, so I'd like to remind you that we do record these programs, and so you can go to our website, spacecenter.org, and click on Events and Thought Leaders, and it will be live on our website probably within 24 hours. So you'll be able to view their presentations and the Q&A presented this evening. I want to remind everyone that our next program will be taking place on February 25th, and we'll be looking at lessons learned from past disasters. In the space program, we'll be focusing on the Challenger, Columbia, and Apollo 1 disasters that took place. And also watch out for our Space on Screen series. This is again part of our recognition of the Apollo year. We're going to be showing The Right Stuff, 2001 Space Odyssey, and Hidden Figures in the coming months. So again, thank you all for joining us and have a great evening. We look forward to seeing you at a future program.